Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the 22nd lecture on the course Maritime Structures under Fire, Blast and Explosion. So it's a sequel lecture what we did in the last one where we discussed about introduction to blast loads, how an explosion damage can be computed using the scaled distance and the peak overpressure calculations from the charts and the design tables. So this is a very interesting reference book which you should have a copy, which will give more detail about the design of structures under fire and blast. Of course, these two are also equally good because they talk about fire resistant design in detail, which you will be using. Okay, now the question comes, let us see how the structure behaves under blast. Structures actually respond differently to blast loads. So I can say the response of structures to blast loads depends on 1. The geometric form of the structure, 2. The enclosure at which the structure is located, and then the orientation of the structure to the explosion. Is it direct, is it on sideways, topways, etc. So, for blast piston design, structures are broadly categorized into 2 types. So, I want to categorize or classify structures on blast resistant design into 2 types. First one is diffraction type structures. The second one is drag type structures. Now, let us see quickly each one of them briefly. Let us talk about diffraction type structures. These are those structures which has, let us say, minimal opening. And the blast happens or occurs on the surface where there are no openings. It means the exposed area receives the blast completely. The total area receives the blast completely, and it experiences the incoming shock wave fully. So, they have 2 components of blast loads. One, what we call shock wave overpressure, which is expressed as PSO. This is the pressure resulting from the sudden rise of air pressure due to the blast front. So, this is sudden release of pressure due to the blast front. The second is dynamic pressure Q. This is the pressure caused by the movement of blast wind. This is caused by the movement of blast wind, which actually follows the shock front. So, since the full face of structure is exposed to waves, since the full face of the structure is exposed to shock waves completely, since the full face of the structure is exposed to the shock waves, the reflected pressure is amplified to the maximum. Therefore, the resulting loads are often high. These structures require detailed blast analysis and strong reinforcements to counteract the effects of this. So, the examples of these kind of structural design could be reinforced concrete walls, enclosed steel frame buildings, and storage tanks or shelters. The other type of structure, as we saw, is called the drag type. Drag type structures are open frame systems. They are made up of small components such as beams, columns, frames, bracings, trusses, etc. Essentially, it is an open frame building. It is transparent to the blast waves. So, these structures have very small projected areas. Directly to the blast. Therefore, the effect of blast on such structures are minimum. Because of the minimal projected area, the shock waves passes through the structure and therefore it exhibits low reflection because it passes through the structure. These structures are primarily subjected to dynamic pressure. Indicated by Q, no reflected overpressure, and this is caused by the fast moving shock wave. Okay. Now, the designs of these structures should focus on one, reducing wind induced forces. Two, minimizing drag coefficients caused by wind. Thirdly, it should ensure stability for slender members. So, I can give few examples. Few examples could be one, pipe racks, two, steel towers which are used for transmission towers, open industrial frames which are classical examples of jacket structures and topside of offshore drilling platforms. The distinction between your diffraction and drag type, let us say that your diffraction type structure and a drag type structure, the primary difference between them is the geometry. So, therefore, one should select the right approach for design, because in diffraction type structures you will have reflected overpressure followed by the shock wave, which is Q, dynamic pressure, whereas in drag type structures reflected overpressure is practically absent because the structure will pass through the shock waves will pass through the structure. Therefore, you will have only dynamic pressure given by Q. So, one has to be very careful in choosing the design perspective of this. Suppose if you have a closed rectangular structure, rectangular structure, let us talk about the effect of the blast load on the front face. Let us assume the type of the structure is a diffraction type, that is a solid structure, no opening or minimum opening. Now, the front face of the structure receives the blast. Wave, okay, and it reflects the blast wave to the maximum to cause peak overpressure. So, the peak reflected pressure which I call as PRA at any point on the front face is given by PRA is given by CRA of PSO, where PSO is the peak side on overpressure and CRA is the reflection coefficient which depends on the angle of incidence alpha and the intensity of PSO on the structure. Now, the value of peak side on pressure is obtained from the standard blast charts. So, the PSO is obtained from the standard blast chart, which I will show you now, which can be used, and this blast chart can be of different types. It can be spherical, hemispherical detonations. We already saw them in the previous lecture, how about they vary, and they are all depends on the scaled distance. The scale distance, of course, you know, is a function of the stand-off distance R. Okay. So, in practical design, the spatial variation of pressure across the front face is neglected. Okay. In design, the spatial variation of pressure across the front face. Front face is the first face which reaches the maximum pressure, okay, is neglected actually in design. It is considered to be uniform throughout the entire area. The entire surface experiences the same pressure at an angle 0 degrees to the shock wave. This assumption is conservative, of course we know that, but it is consistent load for structural analysis and detailing. Let us see how this figure looks like as we see here. So, this is a positive phase shock for a spherical TNT explosion in free air. So, one can look at this, that the reflected and the peak side on pressure are computed for different scale distance if you know the velocity and if you know the values of IRIS. So, the variation of these variables with respect to scale distance is plotted. As you see here, let us for example take the peak side on overpressure. The scale distance increases, okay, it significantly reduces, which we know. Similarly, the reflected pressure decreases significantly further with increase in scale distance, and scale distance is actually measured in units of meter per kg to the power 1 by 3. This is for a spherical TNP explosion in air. If you look at alternatively the positive phase shock wave parameter for hemispherical explosion, then the variation is different for the side on pressure and the peak over pressure or reflected pressure, sorry. Okay. So, these two figures gives us the variation of positive phase shock wave. Remember, I am not talking about the negative side, only the positive phase. If it is spherical TNT, if it is hemispherical TNT on the surface for diffraction type buildings. Okay. Once you know this value, then one can compute the reflected overpressure. On the front face of the building receiving the maximum shock wave. Okay. Now, the duration at which this happens. So, the pressure decreases from its peak value, which is reflected over pressure, to 0, is it not? Over a time. We have already seen that curve, is it not? We have already seen the curve. It goes high and then comes down. So, this duration over a time. If we want to find that time, I should say TRF is given as 2 IR0 by PR0. So, for a given scale distance, if you know the scale distance, because scale distance can be computed if you know the stand up distance, we already seen the equation. So, if you know the scale distance from this curve, whether you assume spherical or hemispherical detonation or TNT explosion, one can compute for a known scale distance the IR value which is required, IRO which is required. IRO variation is like this, which is I am plotting the curve, it is this curve. Okay. So, for a known scale distance, I can always compute the IRO which is required, and I can also compute the peak reflected overpressure. So, based on these two values, can compute the time for reflection, which brings this pressure wave to practically 0. Okay. So, in this equation, PRO is the peak reflected overpressure at alpha equals 0, that is angle of incidence is 0, and IRO is called the reflected impulse at the same location. Both values can be obtained from the blast chart. Blast chart can be used to obtain both the values for both spherical and hemispherical detonation. If you know the scale distance, you can compute this. Similarly, friends, I can also compute something called stagnation overpressure. One can also compute something called stagnation overpressure. which is indicated as PS. This occurs near the edges of the front face. This is going to cause lot of effects on the corner of the buildings, okay, and this stagnation overpressure also drops from its peak value to practically 0 at a time called T0F, which can be computed as T0F is given as 2 ISO by PSO, where PSO is the peak side on pressure and ISO is the instant impulse. At the same location, at any point on the front face of the closed structure, the reflected overpressure, let us say at any point on the front face of the structure, which is a specific type of structure. In this case, we are talking about diffraction type, the closed flat surface, the reflected overpressure begins to decay from its peak value the peak value what we say is PRO to a lower value equal to the stagnation pressure, which is indicated as PSO. So, I can always find the pressure at any point on the front surface is given as PSO plus CD times of Q naught, where and one can also find the time at which this drop happens. Is given as TCP, and TCP is given as 3S by U, where S is the shorter dimension of the building. It can be either height or half of the width, whichever is least, and of course U is the shock front intensity in meter per second, speed of the shock wave. So, I can now use the standard blast charts to find out this value. Look at this chart, can also find the peak shock intensity if I know the scale distance. Let us say for example, this is the dotted one. So, if I know the scale distance, can always find this value. Okay. So, I can find this equation or this value from the equation, and of course, yes, the geometric dimension. I can find the time at which this drop happens from the peak reflected overpressure to stagnation pressure using this equation. I can compute this. Okay. Now, this equation defines the local clearing time at any point. However, to assess the load over the entire face, we must use something called average clearing time. Okay. If you want to find the effect of this on the entire face, one should use something called average clearing time, which is called as TCR, which is given by 4HW by CR times of W plus 2H, where CR is called the velocity of sound in the region behind the shock wave front. And H and W are actually height and width of the building, of the front face of the building. Okay. The clearing effect plays a crucial role in the analysis of blast because this limits the effective duration of high reflector pressure on the structure. So, using these time estimates of TCR and TSOs, one can find the net impulse acting on the wall, which can be used for the structural design. So, using the time estimates, one can compute the net impulse on the front face, which is used in structural design for blast. Okay, that is what we are looking at. Having said this, let us now look at how this variation happens graphically. So, look at this curve which is shown on the screen. The variation of reflected overpressure at a point on the front surface of a reflecting wall. You can also look at the sound velocity in reflected overpressure region. How does it vary with peak instant overpressure? With PSO, how the sound velocity varies with the increase of this. So, this figure will understand that in meter per milliseconds. So, one can see that the reflected overpressure drops and then comes to TCP. We have already seen how to compute TRF and TCP, the time variance of this. So, one can also say the ideal condition could be that this is dropping down and then instead of taking this TCP, take it to time 0 off and you can compute this time from the previous equation what we discussed. Okay. So, we discussed these time estimates. This will tell me what is the time taken for the reflected overpressure to drop and then becomes 0. Okay. Q is the dynamic pressure, CD of course the coefficient talking about this, and PS is the shock wave pressure which we computed. Okay. So, the net loading on the front face. For example, our front face comprises of W into H. W is the width and H is the height of a rectangle. It of course depends on TOF, that is the figure says, okay, TOF, okay, that is the, and of course it depends on also the time clearance TC, okay. So, now let us take two values, the clearance time TC and the stagnation time TOF. If TC is less than or equal to TOF, then the reflected pressure clears before stagnation pressure. Okay. If TC is more than T0F, then the stagnation pressure first decays. Okay. These conditions show how the reflected overpressure transits to the stagnation pressure over time. That is, the reflected overpressure transits to stagnation pressure over time, and that is what the curve indicates. Okay. The reflected overpressure transits to stagnated pressure over time. Okay. That is what the figure indicates. Therefore, friends, the required parameters now to calculate are as follows. One, I need to compute PRO, which is peak reflected overpressure. Then I should require PSO, which is called peak side on pressure. Then I require Q naught, the dynamic pressure, which is the peak value, the peak dynamic pressure. Then I require IRO, which is reflected impulse. Then I require ISO, which is called incident impulse. All of these values can be obtained from the blast chart which I showed you for hemispherical and spherical discharges. Okay. The details of course are given in IS 4991, Indian Standard Code of Practice for blast loads. Furthermore, friends, the net pressure time relationship can be also obtained by calculating the design blast impulse on the structural response. Look at this figure. I can either use the reflected overpressure drop to become T naught, or can use even this straight away and get an equivalence. So, reflected overpressure history on the front face of a closed rectangular structure can be idealized by two forms. So, using any one value of this equation or this model, I can always find the time taken for T0F for the reflected pressure to drop down, or the stagnation pressure to drop down prior to the reflected pressure, depending upon the case as it was discussed. So, using the pressures of actual explosion, the average loading on the face WH is shown here. So, what is the average load for which the structure should be designed? The face is W into H. W is the width of the wall and H is the height of the wall. So, the time what you see here is measured from the instant of shock wave, strikes the front face. The travel time of the shock wave from the front to the rear face is given by L by U. So, L by U, I write it here, is the travel time of the shock wave from the front of the structure to the rear. The pressure rise during this travel on the back face is equal to 4S by U. That is what we see here. The pressure rise is given at this time. So, pressure rise time I should say, okay, pressure rise time is given by this value. So, friends, the average pressure time history for the roof and side walls are also given by this figure. So, the average pressure diagram for the roof and side walls are given by this figure, where the case Td is greater, when the case Td is greater than transit time Tt, is actually L by U. This is transit time Tt, which is L by U. So, I should write it here, the transit time Tt is given by L by U. Okay. So, for the case when Td is greater than the transit time, the average pressure is given by this equation or this figure. Okay. So, friends, if the structure is subject to oblique waves, the blast waves can also act at an angle, then in such cases, the peak reflected pressure is computed as a product of incident pressure and reflected coefficient. And for that angle of incidence with varying from 0 to 90, one can find always the coefficient Cr alpha given by this curve. For any specific angle of incidence, you can always find this value for side on overpressure given in the curve. So, if you know the side on overpressure and if you want to compute the reflection coefficient, pressure coefficient for any angle of incidence, you can use this. Okay. So, the simplified pressure history is given by this equation as we discussed. Then once I know this effect on the structures, then one can always compute the effect of these ground shocks on the coastal structures given by this equation. So, the crater is formed from the underground explosion. The mechanism of formation crater is related to properties of air, soil and interface. They depend on type of soil. The radius of the crater can be calculated using this equation, where Rc is the radius and W is the weight of the explosive and K star is the coefficient proportionality, which can be computed for a different kind of geomaterial as you see on this table. Having understood this, we can now calculate the ground shaking intensity, the scaled peak particle displacement, peak velocity and soil pressure as given by these equations, where R stands in this equation as standoff distance, where wherever we see R, standoff distance, and W is the explosive weight, rho is the soil density, C is the seismic soil velocity, N what you use here is the attenuation coefficient, and F what you see here is the coupling factor, which generally taken as 0.14 for explosives placed above the ground. So, one can find the scaled peak particle displacement, velocity and soil pressure caused by the explosion on the surface, which is given by these equations. So, soil properties to compute shock parameters like seismic velocity, acoustic impedance, attenuation coefficient, because you need them in this equation, okay. So, for different soil categories of loose, dry, sandy loam, dense sand, etc., all these values are given in a selected table which is extracted from the literature for your benefit. Furthermore, I can also compute something called peak particle velocity if I know the standoff distance and the explanation mass, explosive mass, which is given by this, and the attenuation again can be computed based upon type of soil. So, the peak particle velocity shall not exceed the following values, and for different type of rocks the unit weight, compressive strength, tensile strength and create particle velocity is also given for a different level of damage, as you see the geotechnical effect caused by explosion. In case of coastal and other structures above ground, the peak particle velocity measured at foundation level shall not exceed the upper limit, as we see here, for different kinds of structures. If you want to find the effect of blast on different kind of structures, as a summary, we have seen there are two types of structures, the diffraction type and the drag type. We have also seen how to compute the pressure variation on the front face and then the side face using these figures. We have also seen how the overpressure drops to a stagnation pressure. We have used these equations. We have also seen the alternate of finding out this for different time scales, as you see from this equation. Then we have also seen the idealized value of reflected overpressure history on the front face of a diffraction type structure, which is calculated from these two figures equivalently. And we have also seen how the effect is cast on the rear face if I know the time at which the peak overpressure occurs. And one can also find the effect of this explosion on roof and side walls, as you see from these two figures. So friends, let us come to the summary of this lecture. In this lecture, we learnt about how to compute the blast wave effects on rear side, front face, top face of any structure. Usually it is diffraction type, the solid structure. We have also found out the effect of ground explosion on the structures, including the foundation, including the soil effect caused by these explosions. So friends, design of blast resistance depends on what is the type of structure, is it diffraction type or a drag type. It depends on the geometry, the explosion angle and the standoff distance at which the source of explosion from the target is measured. So the equations for governing and computing these pressures are now known. Once you know the pressure acting on a specific surface, you know the stress caused on the surface, you can define or design this system for that pressure. Okay. We will also know the pressure and the time at which this pressure wave will reach the structure. So one can also plan for emergency response planning guidelines based on this time which we have computed. Hope you have followed the sequel of the lecture on blast resistant design. We will continue this further in the next lecture. Thank you very much. Namaste.